students, you have learnt the constructional features of DC machines and then the working principle of DC machines as generator and motor. So, you have studied that how exactly the EMF equation you are going to derive by using the fundamentals of Faraday's laws of electromagnetic induction, Fleming's right hand rule for the generator, Fleming's left hand rule for the motor. So, now you see that how exactly we are going to represent equivalent representation of DC machine. So, I already told you that to work as a DC machine you require mainly the two parts. One is field system, another one is armature. This field system we are going to consider it as a stator, and then armature we are going to consider it as a rotor. So, this field system has the windings, it is wound on the pole, it has to be excited by a small DC source to produce the magnetic field, and the armature can be equivalently represented with the circle like this. So, you can represent it is A. We know that armature has conductors. Since there are conductors, so it should follow the property of conductor, that is it has to allow the current to flow in it. So, in the conductor the resistance is very less, because we know that V is equal to IR. So, R is equal to V by I. So, to make this current to flow, so and when you are considering this relationship between resistance and current, this will be inversely proportional. So, to make the current to flow properly, the resistance should be very low. So, that is why this armature has very low resistance that can be represented as RA. So, what we are doing is the internal resistance of the conductor we are connecting in series with this. When we are representing the terminals, here positive and negative. So, after this the generation of EMF, when the circuit is closed with the load, the current will flow. The voltage across these two terminals we are going to consider it is terminal voltage V. This is the load. So, this will have some resistance, thus we are going to represent it as RL. The EMF induced in this conductor we are going to consider it as EG. So, last class you have seen that how exactly we have derived the equation for EG. This EG depending on the number of conductors, the revolutions per minute, then flux per pole, number of poles divided by 60 into the number of parallel paths. So, the number of parallel paths A is equal to P in case of lap connected. So, A is equal to 2 in case of wave connected. So, the equation of EG you are using to calculate, so this the voltage generated in the armature. Okay. This is how we are representing the equivalent circuit of DC machine. This A represents armature, RA is the internal resistance of the armature, that is of resistance of the conductors. So, here I have shown by that arrow. So, it is from the voltage is rising from negative to positive. Always in the sources we will consider the current will enter the negative point. So, that is lower potential, and it will this leave at the higher potential, that is why it is negative positive. So, the terminal polarities we have represented it is positive and negative. And then what is the equation of this voltage, terminal voltage V in terms of this generated voltage EG. So, when we are going to apply the Kirchhoff's voltage law to this loop, When the load is connected, now this loop is closed. Okay. So now we know that always in the passive element, the current will enter at the upper potential, leave at the lower potential. When we are applying this KVL, so that is the sum of the voltages in the particular loop is equal to 0, means the sum of the voltage rises is equal to sum of the voltage drops. Here there is voltage rise because current entering at the lower potential, leaving at the upper potential. So this is Eg is equal to, when this is current is entering at the upper potential, leaving at the lower potential. So it is, suppose if you are considering this is current IA, the armature current IA, that is equal to load current IL in this case. Okay. So now the voltage drop is IARA plus, here in this the current entering at this through this load and then leaving at the lower potential, plus V. I already told you that there are brush contacts, that is to collect the current. So voltage drop you are going to get across the brushes, that is you can write it is brush voltage drop. And then if you are considering the armature reaction, you have to consider that armature reaction drop also. This armature reaction you are going to study mainly in third semester. Now you consider only this IARA, that is the voltage drop across the resistance of the armature, then the terminal voltage and the brush drop. So this is the equation of Eg. Suppose if brush drop is negligibly small, you are going to consider only Eg is equal to V plus IARA. Under this condition, the terminal voltage equation V is equal to Eg, generated voltage, minus the resistance, that is armature resistance drop, that is V is equal to Eg minus IARA. This is how we are going to express the terminal voltage equation in terms of induced EMF. Now, you see that classification of DC generators. The classification of DC generators mainly depending on how exactly we have connected that field winding and armature winding. So this can be this, when we are considering that network connection, mainly we will see that whether it is series connected or shunt connected. Okay. So now when we are considering that connection, there are mainly two types, that is separately excited DC generator and self-excited DC generator. In separately excited DC generator, we are exciting the field by using that excitation system, that is a voltage applied, that is equal to Vf, that is a DC source we are using. Then with respect to this armature, so we are considering the terminals AA. A represents the positive terminal, AA represents the negative terminal. The usual representation of the field coil you are going to represent with Z, ZZ or F, FF. You can use this F also for this. These are the electrical terminologies what we are using. And then you are going to give the excitation voltage, that is Vf, from the DC source. And then you are going to connect the load across this. When the load is connected, the current I L flows, that is equal to IA in this. So you are going to represent RA this along with this, if you are not writing externally, by representing the equivalent resistance value in series with the armature, you can represent like this also. So this represents the internal resistance of the armature, that is the armature conductors. So, next current IA is flowing in this direction, this is the load. Then in this case also these are the terminal points, the voltage across these terminal points you are going to consider it is V. So, this is the equivalent representation of separately excited DC generator. Now, you have to see that what is the equation of terminal voltage in terms of this induced EMF, and also what is the load current, and then what is the power developed in this armature, and then what is the power delivered to the load from this armature. Okay. So, now since this load and armature both are connected in series, the armature current IA is equal to load current IL. And then I already explained to you how exactly you have to get this V. So, now terminal voltage equation, that is V is equal to Eg minus IaRa if you are neglecting the brush drop and then armature reaction drop. So, now what will be the power delivered, that is power developed in this armature, that is power developed in the armature P is equal to the voltage generated multiplied by this armature current Eg into Ia. Now, what is the power delivered to the load? The power across this power delivered to the load is voltage V and then current flowing through this, that is V into IL. How exactly we are arriving to this point? Okay. Power delivered to the load, when you are going to consider, the power developed is Eg Ia, but not fully it is delivering to this load, there is a copper loss in these conductors. So, that is why power delivered to the load you are getting this is equal to Eg Ia, this is the power developed, minus the copper loss Ia square Ra. When you are taking this Ia as common in this is equal to Ia into Eg minus Ia Ra. So, we know that Eg minus Ia Ra is V. So, this is equal to V into Ia. Since this armature is connected in series with the load, Ia is nothing but IL. So, this is equal to V into IL. So, this is, that is V into IL is the power delivered to the load from this armature. This is how we are going to derive the equations for armature current, terminal voltage, power developed by the armature and power delivered to the load. So, always we are using the units to represent the electrical quantities. For current we are using amperes, for voltage we are using volts, for power we are using watts. These are the standard units to represent current, voltage and power. So, the unit of this power delivered to the load is watts. So, this is about separately excited DC generator. Now, when you are considering the self-excited, so there are three types: shunt wound DC generator, series wound DC generator, compound wound DC generator. In case of shunt wound DC generator, the armature winding and the field winding are connected in parallel. In case of series, the armature winding and field winding are connected in series. As the name indicates, in compound wound, it is depending on the connection, how exactly we are making, whether it is shunt and series. Both the connections we are going to do it in this case, but with different combinations. So, now you consider this shunt excited DC generator. Since I already told, it is the self excited. So, what exactly you are doing is you are going to connect this armature in parallel with shunt field. So, shunt field resistance. So, here you are connecting the armature, you are representing the armature resistance RA, current IA will be flowing in this direction, then the EMF induced is EG, and then the shunt field, it is a constant system in the DC machine. So, you are representing, this is shunt field winding, the resistance of this you are representing, it is RSH. So, then when the load is connected, the circuit is closed, then the current will flow in this closed circuit, that we are going to consider as IL. Then we know that this is current IA. Now, according to KCL, that is Kirchhoff's current law, sum of the currents at the particular node is equal to 0, means sum of the current entering the node is equal to sum of the currents leaving the node. This is ISH. The current flowing through this shunt field, we have considered it is ISH. The current flowing through the load, we have considered it is IL. Then the voltage across the terminal, this is V. Now, we have to derive the equations for IA. Then what is the power developed in this armature, and then what is the power delivered to the load. So, in this, as we see in this diagram, the current IA, armature current IA, according to KCL at this node A, so this is sum of ISH and IL, because current leaving at this node A is ISH and IL, current entering this node is IA. So, this IA is equal to ISH plus IL. This is a shunt field, current flowing through the shunt field and current flowing through the load. Then what is the equation for that terminal voltage? Terminal voltage we have, that is V is equal to EG minus IA RA. So, and then power developed is equal to EG into IA. EG into IA, these are the equations. And then you have, that is power delivered to the load, it is same as that previous, because the load is connected across this EG. Then when you are going to find out the current flowing through this shunt field, see that this shunt field is exactly in parallel with the load, and you know that what is the voltage across this load, that is the terminal voltage V. So, you can calculate the current ISH by using the equation, that is voltage across this is same as the voltage across the load. You know this resistance of the shunt field, you can calculate ISH by considering V divided by RSH. This is in terms of amperes. This is how you are going to get the equation for this armature current, that is IA is equal to ISH plus IL. So, if you know the voltage across this terminal, you can calculate this ISH if you know the value of this RSH. So, these are the required equations for shunt field DC generator. Now, you see that how exactly we are going to connect that series field. As the name indicates, you have already seen, in case of shunt excited DC generator, shunt field coil, that is a field coil, is connected in parallel to the armature. In case of series, observe this, in case of series, the armature is connected in series with the field coil. So, here the armature A is connected in series with the field coil. This is called it as series field coil. the resistance of this you are going to represent it is RSE, and then this series combination you are going to connect across the load. The terminal voltage is V, current IA is the armature current, and the resistance is the internal resistance of the armature, and then the induced EMF is EG, and this is the load current IL. You observe in this case the load is connected in series with the armature. So, armature current and load current both are same. Armature current IA is equal to IL, that is load current. So, now the terminal voltage V is equal to what? EG minus, there are two drops now in series, that is one is the armature drop, another one is field drop. So, you can consider this since the current flowing through all the elements are IA. So, armature drop equation is IA RA minus the field drop equation is IA RSE. So, now you can represent this is EG minus IA RA plus RSE. So, this is the terminal voltage V. Then the power developed P is equal to EG into IA, but here when you are going to consider that power delivered to the load, so you have to neglect the voltage drop across this. So, now power P, power delivered to the load is equal to EG minus IA square, the total resistance is RA plus RSE. So, you have to consider, you have to include the effect of field resistance also. This is EG minus IA square, EG IA, the power developed is EG IA, then minus the copper loss of this armature resistance and the field resistance. So, the power delivered to the load is equal to EG IA minus IA square RA plus RSE. This is the equation, that is power delivered to the load in case of series excited DC generator. This is how you are going to connect the armature and the field coil in series with each other. Now, you have seen that series connection of field winding with respect to armature, and then parallel connection like this with respect parallel connection of field coil with respect to this armature. Since it is connected in parallel, it is shunt excited. So, since here it is connected in series, it is series excited. Now, you see the combination of this series and shunt. So, now when you are connecting this shunt field and series field coil in the combination as shunt and series, see with respect to this armature. So, here you have connected that shunt field winding in parallel with the armature. Here the series field winding you have connected in series with the load, but the terminal here what you have considered is same for this. Okay. So, now how exactly you can represent is this is, suppose if you are going to consider this is series, you are connecting the armature in series with this, then this is the common terminal, and then you are connecting that shunt field in parallel with this. Okay. So, now across this you are going to connect the load. This is how you are representing the short shunt. So, this is the terminal voltage. So, now the current, this IA is the armature current, RA is the armature resistance, and then EG is the induced voltage. This RSE represents the resistance of the series field coil, and then RSH represents the resistance of the shunt field coil. See, you have connected this shunt coil exactly across exactly parallel to this armature, and then series you have connected in series with this. This is called it as short shunt. Since you have used both series and shunt, it is compound excited DC machine, but it is of short shunt. Now you see that the difference between short shunt and long shunt. So here in case of long shunt, what you have done is, in series this, with respect to this series combination, that is first you have connected this armature and this series field coil in series, and then this shunt you have connected across this. This is called long shunt. This is how you are differentiating this long shunt and short shunt, how exactly the way in which the series field coil and shunt field coil is connected to this armature. Then we will solve some problems on this different types of DC generators. In this problem, it is given a 110 volt DC shunt generator delivers a load current of 50 amps. See here it is defined, it is 110 volt DC shunt generator, means the terminal voltage V is equal to 110. Then the load current IL is equal to 50 amps. The armature resistance is given. See, I already told you that armature resistance is very less to allow the current to flow in it. It is 0.2 ohm, and the field circuit resistance is 55 volts, because you are connecting that field coil across the terminal voltage. So here you observe this field resistance and armature resistance. The armature resistance is very less compared to this field resistance. So the generator rotating at a speed of 1800 rpm. So the speed of rotation of armature is 1800 rpm, revolutions per minute, and it has 6 poles. The lap wound means it is the number of parallel paths is equal to number of poles, and has a total of 360 conductors. The total conductor Z is equal to 360. You have to calculate the no load voltage in the armature and the flux per pole. First you collect the data given in the problem. So it is shunt generator. Shunt generator means the armature is connected in parallel with the shunt field coil. In the first case, you have to calculate that no load voltage in the armature, means without connecting the load you have to calculate the no load voltage, that is nothing but Eg, because since you have connected this in parallel, it will be Eg. So and also when you are considering this no load voltage, this is Eg minus Ia Ra. Since there is no load connected in this, the current flowing through this loop is 0. So this V is equal to Eg. So now you have to calculate that no load voltage, that is Eg. So V naught. So you can't take that is V, it is terminal voltage Eg, that is minus IaRa. When you are considering this is 0, you can consider this is V naught. This is not exactly equal to the terminal voltage. Now you have to calculate this Eg in the first part. In the second part, you have to calculate the flux per pole. Okay. In the last class, you have seen that what is the equation for generated EMF in terms of the parameter. Eg is equal to Zn phi p divided by 60 A. So here first you collect the given values, that is, so 110 volts, this V is given, the terminal voltage, and it generates. So shunt delivers a load current IL is equal to 50 amps, and then the armature resistance Ra is given. So Ra is equal to 0.2 ohm. Then the field resistance RSH is given. So that is equal to 55 ohms. So the generator rotating at a speed N is equal to 1800 rpm, and then it has 6 poles, P is equal to 6, and since it is lap connected, A is equal to P, that is equal to 6, and then Z is given, Z is equal to 360. For this data given, now you have to find out in the first part Eg by using the equation Eg is equal to Zn 5P divided by 60A, and then you have to calculate the number of flux per pole. So, now after collecting the data given, so now you have to find out, that is phi. To get this Eg, since you do not know this phi, so phi is unknown, Eg is also unknown, two unknown parameters in this, you use this Eg is equal to V plus IARA equation to, since the terminal voltage is given, it is better to use the equation Eg is equal to V plus IARA to find out. Then that will be, when you are opening this, so that will be the induced voltage in this. So, now what will be this? The given voltage V is equal to 110, and then IA given. So, what is the value of IA? IA you can find it out, because RSH is given and then V is given. So, here if you find out this ISH, IL is given, IA you can easily find it out. So, by using this equation, IA is equal to ISH plus IL. What is ISH? The voltage across the field coil is exactly equivalent to this V is equal to 110 volts, because both are connected exactly parallel with each other. So, V divided by RSH. So, it is 110 volts divided by RSH. So, that is RSH is equal to 55 ohm. So, you are getting it is 2 ampere. So, now IA is 2 plus, what is the load current given? 50. So, this is equal to 52 ampere. Now, you have this RA, it is given in the problem, RA is equal to 0.2 ohm, and then you have calculated this IA as 52 ampere. So, now 52 into, that is 0.2 plus 110 will give you the value of Eg. The value of Eg now is 120.4 volts. So, now you have this equation, that is Eg is equal to Zn 5P divided by 60A. You have completed the first part, that is no load voltage. So, V naught is equal to Eg. Now, you calculate phi, that is the flux per pole, from this equation. So, that is equal to Eg into 60A divided by Znp. Substitute the value of Eg as 120.4 volts, and then number of parallel paths A is equal to 6, the number of conductors Z is equal to 360, the number of revolutions per minute, that is 1800, the number of poles given is 6. After substituting and calculating the phi, you will get the value of 0.011 Weber. So, this is how you have to perform the problem, that is how exactly you are going to calculate the parameters what it is required. First you collect the data given and then analyze the system, what type of system it is, and then you calculate that what it is required in the problem. So, now we will come to the next problem. In this, a 4 pole P is equal to 4, and then it is lap wound. Since it is lap wound, A is equal to P, that is equal to 4, and then the revolutions per minute, the speed is 750 rpm, and it is shunt generator and has a armature resistance Ra is equal to 0.4 ohm, and then field resistance RSH is given, it is 200 ohms, and then The armature has 720 conductors, Z is equal to 720, and the flux per pole phi is equal to 0.3 milliweber. Since it is given in terms of milliweber, it is 0.3 into 10 to the power minus 3 Weber. And then if the load resistance RL is also given, it is RL is equal to 10 ohms. What you have to calculate? Determine the terminal voltage V. To get this terminal voltage V, the equation we have in case of shunt generator is V is equal to Eg minus Ia Ra. You have to calculate this Eg. To calculate this Eg, you can use this Zn 5P divided by 60A. So now, after calculating, here you can substitute, and Ra is given. So calculate, and also here load resistance is given, RSH is given. By using the equation Ia is equal to ISH plus IL. This is nothing but V divided by RSH, and then IL. Since you are considering the voltage across, the current flowing through the load is IL, so this will be RL. So this is how we can calculate this Ia. Ia you can substitute in this. Ra, the value is given in the problem, you know that value, substitute that Eg minus Ia Ra in this equation, you can get that terminal voltage. So the equations given, in this case it is shunt connection, because the shunt field is connected in parallel with the armature and the load is connected across the armature. I already told you that Ia is equal to IL plus ISH. You can calculate this Ia, and then you can calculate this ISH by using the equation V divided by RSH. IL you can calculate by using the equation V divided by RL is given, what is the load resistance. So if you are adding this ISH and IL, you will get this Ia. Then you can calculate this V, that is Eg minus Ia Ra, like this. So Eg you can calculate Zn 5P by 60A, substitute all the values it is given. So the total voltage you are getting, it is 750 volt. So in this figure I already explained the shunt field is connected in parallel with the armature. So for that one, the combined resistance you can calculate like that, and also or otherwise, so you can calculate this separately, or otherwise when you are taking this V outside, what will be this 1 divided by RSH plus 1 divided by RL. What it indicates? The shunt field is exactly in parallel with the load. You can calculate this equivalent resistance. So that is V into R equivalent. R equivalent represents this RSH is in parallel with RL. You can calculate this parallel resistance, you can substitute in this, or otherwise you can do it separately like this. To calculate ISH and IL, you can add the values of IL and ISH. So now Ia is equal to the 27.2 amps, then armature drop Ia into Ra. So that is current Ia is 27.2 amps multiplied with Ra, you are going to get 10.88 volts. Then you are using the equation, that is V is equal to Eg minus Ia Ra to get the terminal voltage. The value what you are getting is 259.12 volt. So this is the solution for the second problem. So now we will move on to the third problem. Here one more. The component that is included in this problem, that is called feeder. Feeder, what exactly feeder is? This is the connection between the substation or domestic, or from the station to this, that is distribution station to substation, you can use this. Means the feeder is a circuit which supplies the current from one terminal to another terminal. That supplies the voltage from one terminal to another terminal. So how exactly you are connecting this? A shunt generator supplies a load. The shunt generator is supplying a load of, the load capacity is 10 kilowatt at 200 volt through a pair of feeders of total resistance 0.05 ohm. So how exactly representing this feeder? with the load. It is a shunt generator. So, the representation is same what I have already told you. So, this is the resistance is RA. So, current flowing is IA, then the EMF induced is EG, and then here you are going to connect that shunt field in parallel with this RSH, and then this generator is supplying a load of 10 kilowatt 200 volt through this feeder. I already told you that to supply the power you are using this feeder. So, pair of feeders you are using. So, this feeder resistance given is 0.05 ohm, the load is of capacity 10 kilowatt and then 200 volt, means the terminal voltage V is equal to 200 volt, the power developed or sorry power delivered is equal to 100 kilowatt, and then the resistance of the armature is given RA is equal to 0.1 ohm. The shunt field resistance RSH is given, it is 100 ohm. Find the terminal voltage and generated EMF. So, you have to calculate this generated EMF. So, the capacity is 100 kilowatt and 200 volt. So, you have to calculate the generated voltage. So, now you see that how exactly you are calculating here. In this, the load current is this IL, we have considered it is I, the load current I, current flowing through the load. So, that is to calculate the current flowing through the load, it is 10 kilowatt power, it is supplying 10 kilowatt power. So, 10 into 10 to the power 3, it represents 10 kilowatt divided by 200, it is equal to 50 amps. Then since you are supplying the power through feeder, the drop in feeders also you have to consider. So, it is current flowing through the feeder and also the load is same, because this armature and then feeder and then the load all are connected in series. Current flowing through the feeder is same as the load current. So, it is 50 amps. So, 50 amps multiplied with the resistance will give you the drop in feeders. Then you calculate the terminal voltage. So, terminal voltage, that is V is equal to EG minus IARA, and also since you are considering the feeder, so you have to consider the drop across feeder also. RV is equal to what? That is, when you are considering the terminal voltage equation, V is equal to EG minus IARA, or this is V plus IARA. So, this is equal to EG and then plus IA into feeder resistance also you have to consider. This represents the drop across the feeder, that is IA into feeder resistance. So, now the terminal voltage V is equal to 200 plus 2.5 volts, and then ISH is, I already told you, you can calculate if you know the terminal voltage. So, here the terminal is now, this will be the V, if you know the terminal voltage. So, the voltage across this RSH is also that V. So, you can calculate current flowing through the shunt field winding ISH is equal to the terminal voltage V divided by the resistance of the shunt field. So, this is equal to 202.5 divided by 100, because 100 is the shunt field resistance given in the problem. This is equal to 2.025 amps. Then we know that this current, armature current IA is equal to, armature current IA is equal to I plus ISH. So, you can calculate I is equal to, IA is equal to I plus ISH. Usually we are using this term L as a suffix to this load current. Sometimes we are not going to use, because this is the main current what we are getting. So, you can write this I, or otherwise you can write it as IL. So, now the armature current IA is equal to I plus ISH. So, now it is equal to, according to the calculated value, it is equal to 50 plus 2.025, where 2.025 is the current, that is shunt current ISH, and I is the load current 50. The total armature current is 52.025 amps. Now, the next aim of our problem is to calculate this generated EMF of the generator, that is the equation Eg is equal to V plus Ia Ra. Eg is equal to V plus Ia Ra. You know the terminal voltage you have already calculated in this, plus Ia you have already calculated, then Ra is given in the problem. Multiply this Ia by 0.1, you will get the answer, that is 207.7 volts. So, this is the solution for third problem. Next we will move on to fourth problem. So, here the required data, the calculated data is more in this. You read the problem thoroughly. It is a 4-pole lap wound. This is also a shunt generator. Delivers 200 amperes, means IL is equal to 200 at terminal voltage of 250 volts. It has a field and armature resistance of 50 ohms and 0.0 ohms respectively. Neglecting brush drop, determine the armature current Ia, the current per armature parallel path. So, since it is lap wound, the number of parallel paths is equal to number of poles, that is equal to 4. You have to calculate the current per parallel path, then EMF generated Eg, and then power developed, that is Eg into Ia. So, now in this the connection is same, only thing is this feeder is not there. So, now this is the terminal of the shunt field generator. So, now the values given is A is equal to the value given in this problem, that is A is equal to P, that is equal to number of poles, that is equal to 4. Generator delivers, that is IL is equal to 200 amps, and then the terminal voltage is 250 volts, and then it has a field resistance RF is given, or RSH it is given as, that is 50 ohms, and the armature resistance RA given is equal to 0.05 ohm. So, you have to calculate the armature current Ia, and then you have to calculate Ia per parallel path, EMF generated Eg, and then power developed Eg into Ia. Now, you see that how exactly you can calculate, since you know the terminal voltage, and the RSH. So, you can calculate this V divided by RSH, that is ISH is equal to V divided by RSH is 5 amps. Load current given is 200 amps, then the total armature current Ia is equal to load current plus the field current. So, this is equal to 205 amps. Since it is a lap wound generator, the number of parallel paths is equal to number of poles, that is equal to 4. Then in the next part you have to calculate that current per armature parallel path is Ia divided by A. So, in each path it is delivering 51.25 ampere. So, then armature voltage drop you can calculate, you know the value of Ia and you know the value of Ra, you calculate this armature voltage drop. Then we know the equation EMF generated in terms of terminal voltage and armature voltage drop. You calculate that by using the terminal voltage and armature voltage drop. The value whatever you are getting is 260.25 volts. Then you have to calculate that power developed, P is equal to Eg into Ia. In part 3 you have calculated Eg, that is you are getting 260.25, and then Ia you have calculated the armature current 205 amps. Substitute those values, you are getting it is 53,351 watt or 53.351 kilowatt. If you are expressing in terms of kilowatt, it is 53.351 kilowatt. Okay. So, the watts, this power you can express in terms of watts or kilowatts, or in higher capacity you can express this in terms of megawatt also. So, I will stop at this stage. I will continue the problems in the next class, and also I will explain you in the next class what is the what are the different types of DC machines, what are the different characteristics you are going to get with respect to the generator and motor. Okay. Today I am going to continue with the problems. Thank you very much.